Hey guys, so this lesson is lesson 1 of 6 lessons, new unit, and this unit is going to be all about exponential and logarithmic functions, equations, expressions. So I hope you enjoy it. We're going to start off by talking about repetitive multiplication. Now, what is repetitive multiplication? Well, for example, what if I started off with the number, let's say I started with the number 3, and I wanted to repeatedly multiply by 5. Okay. What's 3 times 5? I'd get 15. Times another 5, I would get, what's 15 times 5? If you said 75, you were right. What's 75 times 5? If you said 375, you were right. Now, that is repetitive multiplication. You multiplied by 5 over and over and over again. What if I wanted to divide by something, though? Is dividing the same as multiplying? What if I wanted to divide a number? Let's say I started with the number 400. What if I wanted to divide by 2 every time? So we're calling this repetitive multiplication. Dividing by 2 is the same as what? If you said multiplying by 1/2, you were right. So what's 1/2 times 400? Also, the word times, or the act of multiplying, can be interchanged oftentimes with the word of. So what is half of 400? What's 1/2 times 200? What is 1/2 times 100? So repetitive multiplication could allow us to get our numbers bigger. It could also allow us to have our numbers get smaller. There is a bit of a difference in how our numbers get bigger and smaller, and this is going to be important. Here, if I keep multiplying by 5, my numbers will get bigger and bigger and bigger and bigger without bound. They will actually approach infinity. Here, however, I do have a bound. My numbers will get smaller and smaller and smaller, but not toward negative infinity. Do you know what they're going to get smaller and smaller and smaller towards? If you said 0, then you were right. Let's go down here and look at example 1. What if we begin with 1 and repeatedly multiply by 2? Okay, so I'm going to begin with the number 1, and we're going to continually multiply by 2. So what's 1 times 2? 2. What if I had done that again? 1 times 2 times another 2. For starters, that's the same as 1 times 2 to the second. It's also the same as 4. What if I multiply by 2 again? 1 times 2 times 2 times 2, which is 1 times 2 to the third, which is 8. And we can just go on and on and on. Here I have 2 to the third power, 2 to the second. This is really 2 to the first. What's 2 to the 0 power? If you said 1, you were correct. And what's 1 times 1? 1. So if I started with 1 and repeatedly multiplied by 2, I would have 1 times 2 is 2. Times 2 is 4, times 2 is 8, times 2 is 16, and we continue. How can we use the mentioned function to model this sequence of values? So the sequence of values, just to reinforce it, was 1, 2, 4, 8, 16, and this is the mentioned function, y equals some value of a times some base amount raised to the x power. If we look back up at what you wrote down for the most recent part, a will represent, well, a really is representing what went in for 1. And 1 is the number we started with. That's where we started our multiplication. So this is going to be called our initial value. It's where you start. Now for the base. This base amount represents, I'm going to list 5 different things here. 1, I'm going to say that it represents the number we multiply by. It's the number we do a repetitive multiplication with. Another way we can get it and calculate the value of it right over here is any number in the sequence, that sequence of values that we came up with, divided by the term before it. So sort of undoing where it came from. Another thing we can list for a bullet point is we can call it the common ratio. And these will all make sense later on. Another thing we may call it is the growth factor. And that's if that number, the base, is greater than 1. Or, if it's not growth, it's a decay factor. And we can't just say that it's less than 1. It's really if the base is less than 1, but greater than 0. Other things you might want to write down. X is the independent variable with domain. Now, is there anything we can't put in an exponent? We could put negative numbers in an exponent. We could put 0 in an exponent. We could put positives. We could put fractions. The domain for X is all real numbers, or negative infinity until infinity. Set notation, interval notation. Y is the dependent output variable. The value of y depends on the value of x that we put in. Another quick thing before we turn the page. When you raise a number to a negative power, do you remember what happens? Do you remember what 2 to the negative first power is? If you said 1/2, you were right. Do you remember what 2 to the negative second power is? If you said 1/4, you were right. We're going to take this equation we wrote down, this function, y equals 2 raised to the x power, which is, importantly, you need to realize the same as 1 times 2 to the x. The formula we wrote on the prior page was y equals a, and what did we say a stands for? If you said initial value, you were right, times the base, which we gave 5 different names. We said it's the common ratio, it's the number you multiply by, potentially your growth or decay factor, raised to the x power. So by not acknowledging that there's a 1 in front, you're going to ignore the fact that a is equal to 1. So we do want to watch out for that. Now we want to know how this appears graphically. When you were younger, you first learned how to make a table of values and use the table of values to make your graph. Let's make our table of values. What is 2 to the second power, where x is equal to 2? 4. What is 2 to the first power? 2. What is 2 to the 0 power? 1. Hope you didn't forget. What is 2 to the negative first power? 1/2. I hope you didn't forget. What is 2 to the negative second power? 1/4. I hope you didn't forget that one either. Now, I'm going to take these values, which are really input-output pairs or ordered pairs, and I'm going to plot them right on here. Over 2, up 4, over 1, up 2, move over 0, up 1, left 1, up 1/2, left 2, up 1/4. If we look from when we learned how to graph parent functions, you'll see that this is 1 unit above my x-axis here. The 2 is telling me I double how far I am every step of the way. 2 units away, 4 units away. How many units away will I be in the next step? I'll be 8 units away. Next I'd be 16, 32, and so on. We connect these dots because this is representing a function where it's an infinite number of x's and y's paired off to create a graph. Now, on this side over here, we're going to have this dotted line. We'll talk about the dotted line later because we're going to get closer and closer and closer to 0. The domain. This graph goes to the left forever, covering all x values here. And this graph, while it gets very steep, goes to the right forever as well. So whether I look at the equation or the graph, the domain is the same. From negative infinity until infinity. For the domain, we always move from left to right. Now for the range goes from bottom to top. How low does this graph go? The lowest the graph goes is 0. Now we don't actually ever hit 0, so I'm going to use a parenthesis, and then I go up toward infinity forever. HA. HA stands for horizontal asymptote. What's the equation of the horizontal asymptote? Right over here. If you said y equals 0, you are correct. Let's make a table of values for example 2. For example 2, if I filled in 2 for x, 2 to the second power is 4 times 4 is 16. 2 to the first power is 2 times 4 is 8. 2 to the 0 power is 1 times 4 is 4. 2 to the negative first power is 1/2 times 4 is 2. 2 to the negative second power is 1/4 times 4 is 1. Now let's put all of this on our graph. Over 2, up 16. Oh man, it really won't fit up 16. Maybe I should count by a different amount. What if I kept this 1, kept this 2, so that's still 2. But what if I counted by, I don't know, let's say 4s? Then this would be 4, 8, 12, 16. I probably could fit one more. What if x was equal to 3? 2 to the third is 8 times 4 is 32. That's 16, 20, 24, 28, 32. Okay, so over 3, up 32. Over 2, up 16. Over 1, up 8. Over 0, up 4. Left 1, up 2. So that would be 2. And over 2, up 1. Interesting. If I connect these values, I have a different equation than my last example. My x-axis I counted by 1s, but on my y-axis I counted by 4s. So what do we notice about this graph? and this graph. They look nearly identical. But if you think about it, so are their equations. For both of the equations, we're multiplying by 2 every step of the way. It's a repetitive multiplication of 2. The main difference was the initial value. The graph takes on the same behavior, and only the initial value changes. If you remember how the number out front is your vertical stretch, it should make sense that you could draw the exact same image and just relabel your y-axis to take care of that vertical stretch. Before we move on, let's do our domain and range. The domain for this exponential and all exponentials will be from negative infinity until infinity, and the range for all exponentials in this form will be from 0 until infinity, and the horizontal asymptote will be again y equals 0. Here we have example 3. Example 3, you may not need a table of values, but let's use it for practice. What's 1/3 to the second power? If you said 1/9, you are correct. What is 1/3 to the first power? If you said 1/3, you are right. What is 1/3 to the 0 power? 1. What is 1/3 to the negative first power? Give it some thought. If you said 3, you were right. What's 1/3 to the negative second power? If you said 9, you are correct. Let's plot these points now. -2, 9, going from the bottom up. -1, 3, 0, 1, 1, comma, 1/3, 2, 1/9. This graph is different from the last examples because from left to right, my graph is going down. Does that impact our domain or range? Our domain is still from negative infinity until infinity, all real numbers, and our range is still from 0 until infinity. The horizontal asymptote also does not change. It's still at the line y equals 0, which is also another way of naming what. If you said the x-axis, you were right. Here is example 4. Let's make another table of values. If I fill in 2, what will we get? If you said 36, you're wrong. 2 times 3 to the second, you would have to do the order of operations. 3 to the second power is 9 times 2 is 18. If you fill in 1, you do get 6. If you fill in 0, you get 2. If you fill in -1, what do you get? You said 2/3, you were right. If you fill in -2, what do you get? If you said 2/9, you were correct. If we were to graph this, -2, comma, 2/9. -1, comma, 2/3. 0, comma, 2, 1, comma, 6, 2, comma, 18 off my graph. And there's our graph. They all look pretty similar. The domain for all exponentials is negative infinity until infinity, and the range is from 0 until infinity. My horizontal asymptote is again y equals 0. Now, if I look at this the way we looked at our parent functions in the past, we recognize it's exponential. 2, we start up 2 units. 3, we triple how far we are from the x-axis every step of the way as we move to the right. 2 times 3 to triple it is 6, times 3 to triple it is 18, and that's where these numbers come from. We have an initial value, we we have a number that we repeatedly multiply by. So start at that initial value of 2 and then multiply by that number inside there every step of the way. Times 3 is 6, times 3 is 18. Put a few points and draw your curve. Let's look at this. Here we're comparing. If we have a times a base to the x power versus a times 1 over that base to the negative x power, what's happening here? Well, we have a few things that some of you may have noticed in the last two examples. A times, I'm going to call this capital B to the x power. I don't want to use lowercase b because we used lowercase b for our horizontal stretches and compressions earlier this year, and I don't want us to get confused. Some books do call this lowercase b. Lowercase b and capital B are different. What do we say happens when we have a negative exponent? There's a few things we can pay attention to. Negative x as an exponent is actually the same as 1 over b to the negative first power raised to the x. Now, negative first power, what happened when we raised things to the negative first power? What was 2 to the negative first? What was 3 to the negative first? What happened? If you said that this flipped over, you were right. It really makes it 1 to the negative first over b to the negative first. 1 to the negative first power is always going to still be 1. And b to the negative first, anything to a negative power, we could just sort of relocate it from the denominator to the numerator, and it becomes positive. We could even move that 1 down and make it positive also. That becomes b to the first over 1 to the first, or b. That means we just have b to the x in here now. So in conclusion, we have y equals a times b to the x. That means that this representation and this representation are equivalent. If that doesn't quite click right now, let me show you it another way. Y equals 3 times 2 to the x is actually the same as 3 times 1/2 to the negative x. If we leave both of these whole numbers right now and this positive exponent, whereas here I take this 2, find its reciprocal, and make this exponent the opposite sign, I will end up having equivalent statements. Graphically, when we graphed parent functions, here I knew that this was multiplying by 2 every step of the way, and I knew it would cause a growth. Here, I knew I was multiplying it by 1/2 every step of the way, and it would make a decay. However, this negative in the exponent, do you remember what the negative in the exponent does to the graph? If you said it makes a horizontal reflection or flips it over the y-axis, you were right. We're going to look at that in a second. Exponential growth versus decay. What is exponential growth? As the value of x increases, so that means we're going to the right. The value of y, well, if it's exponential growth, it increases as well. As the value of x, I guess we should look at it the same way, increases, the value of y, if you said decreases, you were right. So exponential decay will go down as we go to the right, and exponential growth will be going up as we go to the right. Here we're going to do a little bonus description. I'm not going to test you on this. This is just something we're going to have a little chat about. Now this notation here, this is calculus notation for limits. You will see it at the end of pre-calculus. When the limit as x approaches infinity, this is essentially saying what we just said up top. The limit as x gets bigger and bigger as x goes to the right of my function, meaning what is its y value doing? So when the limit as x approaches infinity of f of x equals, well, we said it also increases, so say infinity, comma, the function represents exponential growth. When the limit as x approaches infinity of f of x equals blank, the function represents exponential decay. What does our y value get closer and closer and closer to when it's exponential decay? If you remember to say 0, you were right. Here we're just comparing the two graphs. Here we have an exponential decay. It's getting closer and closer to 0. Here we have an exponential growth. It's going up toward infinity. However, on the left, it also gets closer to 0. And then the decay on the left gets closer to infinity. However, we usually read things from left to right. And in the notation up top over there, we were talking about going toward the right anyway with that infinity. These exponential functions are asymptotic to the x-axis. You could almost think of this word, it comes from Latin, but you could think of this word as asymptomatic. You don't have any of the symptoms or characteristics of something, you don't possess them. So asymptotic means my graph will get really, really close to this line, but it'll never merge with it. It'll never become one with that line. So this line that we get closer and closer to, in this case it's the x-axis. The x-axis is an, do you remember what it's called? If you said asymptote, you were right. A definition down here says, a graph approaches an asymptote, so here's my graph, either the pink or the blue, as x or y, one of the, either the output or the input increases in absolute value. So I don't mean increases towards only positive infinity, as one of them goes out towards negative infinity, as something goes up forever, as something goes to the right forever, or as something goes down forever. Absolute value just disregards that negative. It just sends it in one extreme direction. In conclusion, for the function f of x equals a times b to the x, such that a, well, we have a few things we have to say about a. A cannot equal 0. If b is greater than 1, the function represents exponential growth. If b is less than 1, but greater than 0, the function represents exponential decay. In either case, where is the y-intercept located, whether it's growth or decay? The y-intercept is always located at 0, comma, a. In either case, the domain is always negative infinity to infinity or all real numbers. The asymptote is horizontal with equation y equals 0. The range is always from 0 until infinity. And as for the x-intercept or intercepts, there are none. Because of the asymptote being on the x-axis, there are no x-intercepts for this type of example. For this example, we need to identify growth versus decay. We're going to find the y-intercept as an ordered pair. We're going to sketch each graph. We're going to clearly indicate 2 points. And we're going to include consideration of the asymptote. So, first examples. 12 times 0.25 to the x. The first part of the directions ask us to identify growth versus decay. Is this growth or decay? If you said decay, then you were right. What's the y-intercept going to be for this particular equation? You said 0, 12. Good job. Now we're going to sketch the graph and include 2 points. One point could definitely be 0, 12. The next point I'll fill in 1. 0.25 to the first power, which is really 1/4 times 12. And we said times means of. 1/4 of 12. That's 1. And that's the point 1, 3. We're not drawn to scale, but that's okay. Here's my y-axis and my x. Is this growth or decay? This is growth. This value here is larger than 1. What is the y-intercept for this example? The y-intercept is 0, 0.075. Now I'm going to draw the graph. Again, we're not going to use anything to scale right now because we're just sketching. If I fill in 1, 2 to the first power is 2, times 0.75 is 1.5. If you cross your x-axis, that's not good because we have an asymptote there. Suppose you made $500 the summer before college. You invested it into an account that pays 4% interest annually. Is this growth or decay? This example is growth. What's my y-intercept in this example? My y-intercept would be 0, 500, because that's my initial value. If I get 4% interest annually, I don't need a calculator. How much will I have after 1 year? Remember, percent means per 100. We have 5 hundredths. We have 4 for every 100, and we have 5 hundredths. 4 times 5 is 20. That right there is exponential growth, the y-intercept of 500. I could even write the equation if I wanted to. 500 is my a times something to the x. Do you know what needs to go in the parentheses for this kind of example? You're a big winner if you said 1.04. 0.04 would just be finding 4%, and that would be decay. 4 would quadruple the amount. This here represents 104%. It keeps the original amount and tacks on a 4% increase. Is this growth or decay? What's your y-intercept? What's this ordered pair? Is this growth or decay? Our y-intercept would be here we're finding what percent of 700? We're finding 80%. One way to do this without a calculator is 700 times 80 over 100. Think smarter, not harder. And we'll get 1, 560. Here's our next example. Be sure you always press pause if you need to copy something down so you don't miss any explanation. Let's say you start your own small business the summer before senior year. After spending $800 of your own money, your revenue at the end of 1 year totals $1,280. Your business profit sees a 5% gain annually for the next 6 years. Is this growth or decay? Definitely growth. Now we're going to model the profit in an equation right now. Y, being the profit, equals the initial profit times my base to the x. What was your first amount of profit that you made on year 1? Your profit year 1 was $480. Revenue is the amount of money that came in. Profit is what's left after you take away all of the money to pay back your cost. That leaves us with $480 profit. If we're going to see a 5% gain, what number goes in the parentheses? 1.05 makes you a big winner this time. That's 105%. If I wanted to figure this out without a calculator, 5% means 5 for every 100. I have 4 hundreds. That means 5 for the first, 5 for the second, that's 5 for the third 100, and 5 for the fourth 100. Now, 5% of 80. Well, 5 is out of 100, so it's really 4 out of 80. So without a calculator, you can get 24. So at 1, I'm tacking on 24, which means 504. So your profit would be $504 the next year. This is all we're going to do today, and I'm going to attach some homework on our Google Classroom that will involve practice of examples like this. Please read the post on Google Classroom very carefully so you know what the requirements are for submitting your work. I hope you took really good notes. I also need you to take a picture of your notes and submit them on Google Classroom for a classwork grade as well. I hope you liked the video and I hope it helped you out. And I'm trying to make small lessons every day so that we can get through this time as best as possible. Stay healthy.